Let us begin our understanding of the mathematics behind initial value problems by considering a very simple differential equation. This is in standard form because you have only the first derivative, and dy by dt is equal to some function f of y. The functional form f of y is given to us. So dy by dt is equal to f of y, and the value of y at time t is equal to t naught is specified to be y naught. So this is the initial condition. This is the differential equation in standard form. So this is IVP in standard form. Now what we are asked to do is, given the differential equation and the initial condition, we are asked to find out the values of y at specific times t1, t2, t3, t4, tf. We could have this t1, t2, etc. as closely spaced as possible or as wide apart as possible. The step size, that means the gap between t1 and t2, is our choice. In any case, we have to get these values of y at these specific time points. So we are not going to get an algebraic expression for y as a function of t. We are going to get numbers for y at t is equal to t1, y at t is equal to t2, y at t is equal to t3, and y at the final time tf. So we are going to get a bunch of numbers, a sequence of numbers, as the answer to the problem. And this would represent an approximate solution to the true solution, which is yt. So if you were to solve it analytically, let's say f of y was linear, or if it was a simple nonlinear form, we would be able to get the true solution yt, which is also the analytical solution. But in other cases where f of y is complex or nonlinear, all we can hope for is to approximate this differential equation by an algebraic equivalent using finite differences and solve that approximate equation to get the solution yt1, yt2, ytf, as I explained earlier. So in short, you can call yt1 as just y1, yt2 you can call as y2, and y at tf you can call as yf. These represent the solution at discrete time points, not at continuous time points, as would be the case in an analytical solution. But here we are going to get the solution of y at discrete time points t1, t2, tn, etc. These points can be evenly spaced or it can be unevenly spaced. The choice is ours. But for simplicity purposes, we will go with equi-spaced points. So the gap between t1 and t2 is, let's say we call it as h, or delta t is going to be the same as the gap between t2 and t3. So we can assume equidistant points without loss of generality. If you want to represent whatever I have said so far as a figure, so the analytical solution will be like this. You will have an expression for y as a function of the independent variable x. So y you can get as a function of x. Starting from dy by dx is equal to f of y, and y at x is equal to 0, let's say, is given as y naught. So starting from this, you would be able to solve it using pencil and paper or computer algebra, and you can get the expression for y as a function of x. So an equation, if you like. And then you can plot the equation at any value of x that you want, and therefore you will get this continuous looking line. So this is the analytical solution. With the numerical solution, where this f of y is the hard one, we would not be able to get y as an equation in x. As mentioned earlier, we would invoke the idea of finite differences and solve the problem for values of y at different time points. And we can represent the solution as the sequence of dots. So the numerical solution will just produce this value at t is equal to t naught or at x is equal to x naught, and then it will produce this value of y that stands for t is equal to t1, or let's say x is equal to x1, and so on. So all we get is these kind of points that are represented as circles. And then if you want, you can just join them by a curve to get something that looks like this. So just want to say that the numerical solution will not look like this, which is the analytical solution. It will look as a sequence of values at specific values of the independent variable. Now, let's look at the Taylor series expansion of y of t around the point t is equal to tn. Please note here we are considering the differential equation as dy by dt is equal to f of y. So this is the equation we are considering. Now we want to find out the value of y at tn plus h. Our current point is tn. So we know the value of y at t is equal to tn. So this is given. For example, if n is equal to 0, we know the value of y at t naught, which is the initial condition. So we know where we are in terms of the independent variable, and we also know the value of y at that value of the independent variable. So we know y at tn. And using that information and something more, we are trying to find out the value of y at tn plus h. So we are trying to move from tn, you are moving to, let's say, a point tn plus 1, and the gap between these 2 points is h. That's the step size. So I know the value of y at this point. Y tn is known. So my question is, what's the value of y at tn plus h? If I move a little bit along the independent variable by an amount h, how is the value of y going to change? So we resort to Taylor series expansion to answer that. So y at tn plus h is equal to y at tn, the base value, plus y dash evaluated at tn. So this is the first derivative of y evaluated at t is equal to tn multiplied by h. We have looked at this Taylor series many times in the past. Then plus the second derivative of y evaluated at tn, the point around which you are trying to get this expansion. That is, second derivative is going to be multiplied by h squared by 2 factorial, which is nothing but h squared by 2. So if you want, you can have another term y triple dash, the third derivative of y evaluated at tn multiplied by h cubed by 3 factorial, etc. So this goes on forever. What I've shown in print is just the first 3 terms. That means we are stopping after the h squared by 2 term here, after the second derivative term, just in this equation. Now we always resort to the easier route. We do not want to have non-linearities. We do not want to have higher order derivatives to be evaluated, etc. So as a very crude approximation, I can stop with this term. That means include the constant term and include the first derivative term. These are all to be ignored. And note that the leading term here is h squared. So if I truncate at this point and just use this as an approximation, this will have an error of the order of h squared, because that's the leading term in what has been left out. So the error in this consideration will be of the order of h squared. Now, so this is the equation we get from Taylor series expansion, and we stop after the second term on the right hand side. Now please note that dy by dt, right? dy by dt is equal to f of y. That's our original ordinary differential equation. Dy by dt in short form is y dash. So y dash is nothing but f of y. And y dash evaluated at tn would be the value of f evaluated at yn. It's the same. Therefore, I can write y tn plus h as y tn. So these terms are retained. And y dash tn, we can replace it by f of yn. Kindly note, y dash is nothing but dy by dt. And dy by dt, our original ODE is dy by dt is equal to f of y. Therefore, when you do that, you can say y dash is nothing but f of y, and therefore y dash evaluated at tn will be the same as f evaluated at yn. Because at t is equal to tn, y is equal to yn. Therefore, we have this equation. This equation is called the Euler equation, and this scheme is called the Euler scheme. So basically it says y at tn plus h is y at tn plus f of yn multiplied by h, where h is the desired or the chosen step size. So if I give you an equation dy by dt is equal to, let's say, y to the power of 2, just as an example, and I say y at time t is equal to 0 is 7. So what we can do is, now we can say y at t is equal to 0.1. So I'm choosing h is equal to 0.1. My step size is 0.1. So given the solution at t is equal to 0, I want to find out the solution at t is equal to 0.1. So y at t is equal to 0.1. So tn in this particular case is 0. H in this particular case is 0.1. So y at 0.1 or y at t is equal to 0.1 is going to be equal to y at t0, which is y at 0 plus fyn. Fyn is yn squared, right? Yn squared, because f of y is y squared. F of yn is going to be yn squared times h, and h is 0.1. So we say y at t is equal to 0.1 is equal to y at 0. Y at 0 is given to be 7 plus yn squared. Yn squared means the value of y at t is equal to 0, because here n is equal to 0 to start with. Therefore, y0 squared, which will be 49, because 7 squared, times 0.1. So this is going to be 11.9. So knowing the value of y at t is equal to 0 and the function and the h value, I'm able to compute the value of y at t is equal to 0.1 using the Euler scheme. Now, if I have to find out y at t is equal to 0.2, I'm going to say y at t is equal to 0.2 is y at t is equal to 0.1 plus y at t is equal to 0.1 the whole squared times h, which is 0.1. So that's going to be 11.9 plus 11.9 squared multiplied by 0.1. You can compute it, and that's the value of y at t is equal to 0.2. So you can keep marching forward in time and evaluate y at those discrete time points. And you can stop whenever you choose to stop. Coming back to what we have in the slide, y1 is nothing but y at t1. So y at t1 is going to be the same as y at t0 plus h, because from t0, if you move forward by h, where h is the step size, you will reach t1. So t1 is nothing but t0 plus h. So y at t0 plus h is the same as y at t1, which in shorthand form is y1. So y at t0 plus h, when you put n is equal to 0 here, you are going to get y at t0 plus h is equal to y at t0 plus f of y0, because n is 0, times h. Therefore, y1 will be equal to y at t0 can be represented as y0, and fy0 is the function evaluated at y0 and multiplied by h. Please note, we know the value of y0 because the initial condition is given. Since we know y0 and we know the function form for f, which is given to us, we can evaluate the function at y is equal to y0. So we can calculate this. We know what is the step size we desire because we determine or we choose what h is. So everything on the right hand side is known, and therefore you can find y1. So the equation is y1 is equal to y0 plus f y0 times h. In general, I can write it as y at I plus 1 is equal to y at I plus f of y at I times h. So if you put I is equal to 0, you're going to get this expression. If you put I is equal to 1, you're going to get this expression. So you can compute y2 now once you have calculated y1, because once you have y1, this is known, and you can evaluate the function at y1. So this would be known, and h is our choice. So therefore, I can find out y2. Once I know y2, I can find y3, and I keep going on until I want to stop. So this is the Euler scheme. This is called a single step explicit scheme. It is single step because it does not depend on what happened at tn minus 1, tn minus 2, etc. It doesn't depend on that. If you give me the condition at the previous time, I can find it for the next time. That's why it's called single step. It is explicit because everything on the right hand side is known. Therefore, there is no iteration or anything like that involved. So this is why it is called a explicit scheme. So that is what is explained here. Now, as I already said, the error in the Euler scheme is going to be of the order of h squared because that is the leading term that was dropped off from the Taylor series expansion. Therefore, the error is of the order of h squared at every instant in time, right? At every value of the independent variable, when you evaluate the dependent variable, you're going to have an error of the order of h squared. And because it is always computed at every step, this is called a local error. So the local error is of the order of h squared. Now, if h is large, the error will be large. Now, as we discussed in the context of numerical integration, we can also have what is called a global truncation error. That means as we go along, what happens to the error? Because at any particular instant, the error is of the order of h squared for the Euler scheme. But as we go along, what happens is the global truncation error will be the sum of local truncation errors over all the intervals. That means the errors accumulate. So the global truncation error is going to be equal to beta h squared plus beta h squared all the way for many times, right? As many times as we are going. So when you go from t0 to t1, you are going to have an error of the order of h squared. So that is 1 times error of the order of h squared. So order of h squared, I can just put a constant and say it is equal to beta h squared, where beta is some constant, which is of the order of 1. When you go from t1 to t2, again, the local error is going to be of the order of h squared. So that is also going to be beta h squared. Now, in going from t0 to t2, we have a total error which is equal to 2 beta h squared. Now, if we extend this idea to tf all the way, right? t0 to t1, t1 to t2, t2 to t3, t3 to t4, all the way till t is equal to tf, you would have accumulated f beta h squared as the overall error. So I just demonstrated in going from t0 to t2, you're going to have 2 beta h squared as the overall error. So if you go from t0 to tf, it is going to be f beta h squared. Now please note that this f, right, it's going to be inversely proportional to the step size h. That means the number of intervals from t0 to tf is going to be f. Now from t0 to tf, I can choose it to be just one interval. I can go from t0 to tf in just one step or 5 steps or 7 steps. So if I use more steps, h will be small. In other words, if h is small, I will have more intervals. That means f will increase. If I have large h, f will decrease. So f is inversely proportional to h. Therefore, I can replace this f by 1 by h. I can call it, if you want, alpha times 1 by h. So f beta h squared becomes alpha times 1 by h beta h squared. So you can call it as alpha beta h, or you can call it as gamma h, or you can just call it of the order of h. So the global truncation error for Euler's scheme would be of the order of h, even though the local error is of the order of h squared. So if you look at this example, this is dy by dt is equal to f of y. So f of y is equal to minus 3y. So f of y naught is going to be equal to minus 3y naught. F of y1 is going to be minus 3y1, etc., etc. And the initial condition y naught is given to be 1. So this is given. So this is the IC. So we are asked what's the value of y at 0.25. Now let's assume that I'm choosing a step size of h is equal to 0.25. So I want to go from t is equal to 0, which is my initial value of time, to t is equal to 0.25, which is my final time. And I want to reach there in one step. So I'm choosing h to be 0.25. Please note this problem can be solved analytically because this is a linear ordinary differential equation. So we can get the analytical expression for this. But let's pretend it's a hard problem and we want to solve it using the Euler scheme that we just learned. Since f of y is minus 3y, f of yn is minus 3yn. And with a step size of 0.25, y at 0.25 will be reached in one step. So y at 0.25 is going to be y at 0 plus fy0 times h. H is 0.25. So basically, I'm using this equation. The value of y naught is given to be 1. F of y naught is going to be f of 1, and f of y is minus 3y. Therefore, f of 1 is going to be minus 3 times 1, which is equal to minus 3. So f of 1 is going to be minus 3 and h is 0.25. So I've just substituted the numbers that corresponds to this formula. And when you do that, you get y at 0.25 to be 0.25. This is what the Euler scheme gives us when we take h is equal to 0.25 for this problem. And the global error is going to be of the order of h, and h is 0.25 here. So this number may be off the true value by as much as 0.25. That's what the error means. Now, if you tried a step size of 0.125, we will go from t is equal to 0 to t is equal to 0.125. So find the value of y at t is equal to 0.125 and then use that as a launch pad to go from 0.125 to 0.25. So the step size here is 0.125. The step size here is 0.125. So let's say we solve the same problem to find out y at 0.25, but we go in 2 steps. So when we do that, the value of y at 0.125 is going to be the value of y at t is equal to 0 plus the function at y0 times the h value, which is 0.125 here. So y at 0.125 is going to be 1, which is y0, that's given in the problem, plus f of 1. F of 1 is going to be minus 3y, and y is 1 when you start off, right? Because y0 is 1. Therefore, f1 is going to be minus 3, and h is 0.125 here. So I get the value of y at 0.125 to be 0.625. So I found out the value of y at t is equal to 0.125. Now, the value of y at 0.25 is going to be y calculated at 0.125 plus the function value at y1. So y1 is 0.625. So that goes here. Because now this becomes like the initial value to calculate the next step. So f at 0.625 times h, and y at 0.125 we just computed it to be 0.625. So this is 0.625, and f of y is minus 3y. So minus 3. What's the value of y at the base point now? The value of y at the base point now is 0.625. So that goes in there, and then this is h. So exactly implementing the Euler scheme. Now, if you put in the numbers, you get a value of 0.3906. So using a step size of 0.125, I estimate the value of y at 0.25 to be 0.3906, which is very different from 0.25 that we got. So a very low order Taylor series expansion and a very high h will lead to bigger errors, as you can imagine. Right? You're doing an approximation of the Taylor series expansion, a very crude one to begin with. And then even there, you are using a very big step size. That is going to be detrimental, because the smaller the step size is, the better is going to be the accuracy. So 0.3906 is going to be a better estimate of y at 0.25. We are still using the first order Taylor series expansion, but at least we used a smaller value of h. So the global error is going to be of the order of h, and h in this case is 0.125. So the error here is going to be smaller than the error that was illustrated earlier. Now, if I use the step size of 0.05, I can go from 0 to 0.05, and then from 0.05 to 0.1, etc., and reach 0.25 ultimately. Now, to do it by hand, we could do it for the simple problem, and we could get to the answer, but doing 5 steps takes some effort. So what we do is we take the help of MATLAB, and this is the small MATLAB code that I write to implement this. So starting time is t is equal to 0. The value of y at t is equal to 0 is given to be 1. That's the initial condition. We are choosing h to be 0.05 here. And I'm starting with the t vector to be just having the element 0. So it has got only one element at this point in time. And then what I do is I say while t is less than 0.25, do it. The moment t reaches 0.25 or it exceeds 0.25, do not do these iterations. So do these calculations only when t is smaller than 0.25. And when we start off, we start with t is equal to 0. Therefore, it will enter this while loop. So the value of y is going to be the previous value of y, and then you append this calculation, which is nothing but the last y value plus the value of f evaluated at the last y value times h. So this is the Euler's scheme. Yn means the last element of y. So when you start off, y is equal to 1. So the last value of y is 1. So what will be appended to y will be y end, and y end we just noted is equal to 1. So this will be 1 plus minus 3 times 1 times h. That is what we did here as well as here. Okay, so this does that. So now at this point in time, y will be 1 because you started off with 1, and now you appended this. So it will be 1 plus minus 3 times 1 times 0.05. So y at this stage, once this statement is executed once, it is going to be 1 followed by 0.85, because minus 3 times 0.05 is 0.15 negative, and when you add that to 1, you're going to get 0.85. So at t is equal to 0.05, we have determined the value of y to be 0.85. So that is what you see here. Then I'm saying t vector, you have to expand it. Previous t vector was 0 because that was the initial time. Now we are going to add h to it. So we started with t is equal to 0. Now this will be 0 plus 0.05. So t vector will now be 0. That's what we started with. Then it will be t plus h. T is 0, h is 0.05. So t vector will be now this. And then I'm going to increment t by h. So at this point in time, t will be 0.05 because the original t is 0. Now it is 0.05. Now what is time? T is 0.05. It is less than 0.25. Therefore, this statement will execute again. Now y will be this, right? When it gets into this statement, y will be now 1 and 0.85, and y end will be 0.85 because that's the last value of y. Y end means 0.85. So now to 1 and 0.85, you will append this one, which will be y end is 0.85 plus minus 3 times y end is going to be 0.85 times h, which is 0.05. So this will be the new value that is appended. So at the execution of this line, you're going to get y to have 3 elements. 1, 0.85 as described earlier, and this calculation will give us 0.7225. So we have calculated the value of y at 0.1. So t vector now will be 0, 0.05 from before. To that you will append t plus h. What was t? T is 0.05. To that you will add h, which is 0.05 plus 0.05, which will be 0.1. So t vector is going to be now this 3 element vector, and y at this time will be this 3 element vector. So everything is fine. T and y are moving in tandem. Now this t will be 0.05 plus 0.05. So t will be 0.1. Now 0.1 is smaller than 0.25. So this set of commands will execute one more time, and so on. And at some point in time, this t will reach 0.25, in which case this statement will become false. Because when t becomes 0.25, t is no longer smaller than 0.25. So the moment you have calculated for t is equal to 0.25, the iterations will stop. And then I can display the values of t vector and y vector, and you will get this to be the answer. So you can readily see the values of t and the corresponding values of y when I used a step size of 0.05. So according to this step size, using the same Euler scheme, I am able to get the value of y at 0.25 to be 0.4437. With h is equal to 0.125, we got 0.3906. With h is equal to 0.25, I got 0.25. So which answer do you think will be more accurate? Obviously the one with the smaller step size. This is going to be more closer to the analytical answer, to the truth. Smaller step size is always going to give you higher accuracy. Now you can compute the value of y at t is equal to 0.25 using a step size of 0.01. That means you're going to reach t is equal to 0.25 from t is equal to 0 in 25 steps. Here we demonstrated what happens when we reach 0.25 in one step. Then we looked at two steps, 0, 0.125 and 0.25. And then we use MATLAB to work with a smaller step size. So 5 steps to reach 0.25. So 0 to 0.05 is one step, 0.05 to 0.1 is the second step, etc. And ultimately we reach 0.25. Now if you want to do it in 25 steps with a smaller step size, hoping for higher accuracy, you can do that. But doing it by hand will be crazy. Therefore, all you do is change this line from h is equal to 0.05 to h is equal to 0.01. That's the only change we make. That's the power of writing a code. So when you do that, you get a value of 0.467, which is different from 0.4437. So as you decrease the step size, the answer changes. And this problem, because you can do a true analytical solution because the differential equation is linear, the true value we know it's going to be 0.4723. So do it by hand and substitute t is equal to 0.25 for t, you will get y is equal to 0.4723. So basically through the sequence of experiments, we have found out that as the step size h decreases, the accuracy of the solution improves. Certainly you would agree that 0.467 is a lot closer to 0.4723 as compared to the answers we obtained with h is equal to 0.05 or h is equal to 0.125 or h is equal to 0.25. Now we can consider a second example where this is the ordinary differential equation. This is the initial condition. Please note this is a first order ODE. So one condition is enough to solve this problem. So this is y naught. Y naught is given to be 2. So y naught is 2. Now the interesting thing here is the right hand side in the standard form, the right hand side should be only a function of y. Here the right hand side is also a function of the independent variable x. So how do you handle the situation? So that's one interesting thing here. Now the question that is asked of us is using a step size of h is equal to 1, so that's also given to us. They ask us to find the value of y at x is equal to 4. So given the value of y at x is equal to 0 to be 2, we have to find out the value of y at x is equal to 1, then use that to find the value of y at x is equal to 2, and then use that to find the value of y at x is equal to 3, and ultimately we want to find out the value of y at the final value, which is x is equal to 4. So we are going to do it in 4 steps. All right. And we are going to use the Euler scheme because only that has been introduced to us. Now this is not in standard form because this is now a function of x and y. So how do we convert it into a standard form? So I'm going to define two symbols. I'm going to say the first symbol y1 is the same as the dependent variable, which is y. And I'm going to define the second symbol y2 which I equated to the independent variable x. So given this, what is dy1 by dx? Because y1 is equal to y, dy1 by dx is dy by dx. And dy by dx is 4 e to the power of 0.8 x. Instead of x, we have to use the symbol y2 minus 0.5. Y is nothing but y1. So the first equation I get out of this new labeling is this. dy1 by dx is 4 e to the power of 0.8 y2 minus 0.5 y1. And the value of y1 at x is equal to 0 is 2. Instead of saying y, I'm calling it as y1 because y1 is the same as y. Now, if y2 is equal to x, dy2 by dx is going to be dx by dx, which is equal to 1. Therefore, dy2 by dx is equal to 1. This is okay. The right hand side should not be a function of anything other than the y's. It cannot be a function of x if you want to put it in standard form. So this is okay. And what is the value of y2 at x is equal to 0? y2 is x. So what is the value of y2 when x is equal to 0? y2 will have to be 0. Because at x is equal to 0, y2 which is equal to x should be 0. So therefore, the initial condition for the second state y2 is 0. So this original problem is now cast as a standard form of ODE for solving initial value problems. So now the question is, find y1 at x is equal to 4. We are not interested in y2. We are interested in what is y1 at x is equal to 4 because y is equal to y1. So this is the new problem. So what you see at the bottom is the new problem that we would solve because this is in standard form. We are going to use the Euler scheme. So we know that f1, the function on the right hand side of the first equation, which is dy1 by dx, the right hand side of that, that's going to be a function of y1 and y2, and the specific form is this. f2, which is the right hand side of the second equation, second ODE, that is equal to 1. So f2 is equal to 1. And for this system, if you invoke the Euler method, you're going to get this expression. Because dy1 by dt is only a function of f1, y1 at I plus 1 is going to be equal to y1 at I plus the function 1 evaluated at y1i and y2i. Because the values of y at stage I is used to determine the value of y at stage I plus 1. So it's exactly the same Euler form, but now instead of one element, we are having two elements in our system, y1 and y2. So we write an expression for y1 in terms of f1 and we write an expression for y2 in terms of f2. So same Euler scheme that we learned earlier, but now an expression is written for y1 in terms of f1 and an expression for y2 in terms of f2. So these are the equations. And you can write a MATLAB code which we'll demonstrate in the next slide to generate this particular answer. So we can get x, y1 and y2. Since y2 is the same as x, we are getting the same numbers for these two columns because y2 is equal to x. But what is important for us is the value of y1, which is equal to y. And it comes out to be the answer for y at x is equal to 4 comes out to be 56.8493. Now, what does the code look like? Very much like what we saw in the previous example. So I'm not going to explain this in detail, but all I'm going to say is it has two components, y1 and y2. So I'm going to give the starting value for y1 and the starting value of y2 given in the problem. That means the initial conditions. For y1 it is 2, for y2 it is 0. So that is what I gave. In the previous example, I gave the initial condition only for y because there was only one y there. In this case, there are two y's, y1 and y2, therefore I have to give both. Then h is equal to 1. I'm just following the same thing that is done here. So h, there I said 0.01. Here the problem says h is equal to 1. And then the starting value of the independent variable is 0. And here the independent variable is x. Therefore I say x is equal to 0. There I said t is equal to 0. Of course, these statements can be written in different orders, right? It doesn't have to follow the same order as long as it is acceptable to MATLAB. It's fine. And here I'm saying x vec is equal to 0. There I said t vec is equal to 0. Here I'm saying x vec is equal to 0. So everything is the same. And then this while loop. There I said while t less than 0.25 because we wanted to stop at t is equal to 0.25. Here we want to stop at x is equal to 4. Therefore, the while command is while x less than 4. Then the expression for y1 and y2 separately. Y1 uses y1 end, y2 end, exactly like we use y end there. And then this is f1. So f1 times h added to the previous value of y gives you the new value of y. And then you append it to the y1 vector. You do the same thing for y2, right? So y2, the function f2 is 1. So f2h is 1 times h. So that is just left as h. So actually there is this f2 here. But f2 is 1. Therefore, it becomes very simple. So these two statements implement the Euler scheme. And to x vec, I add the value x plus h. So when you start off, x is 0. And then now 0 plus h. H is 1. So x vec will now become 0, 1. Because when it comes into the loop, x vec is 0. So it has got one element which is 0, which is the starting value for x. Now after one execution of this loop, so x vec will be 0 followed by 1. And the new value of x will be 0 because you started with x is equal to 0. Once it does this loop once, it is going to be x, the new value is going to be equal to the old value x, which is 0 plus h, h is 1. So now x will be equal to 1. Now 1 is less than 4, therefore these statements will execute again, and so on. And once this loop is over, then I'm asking it to display the results, and that's what you see here. So this output comes because of this. Of course, it will not draw these horizontal and vertical lines. Those I've drawn as my own decoration. But you will get that kind of sequence of numbers that you see inside this rectangle, etc. So this is how simply you can execute or implement the Euler scheme. Now, just like we had the forward Euler method, you can also have what is called the backward Euler method if you implement the backward difference approximation. So let's say you have this dy by dt. I can represent dy by dt as yi minus yi minus 1 divided by h. Please remember what we did in numerical differentiation. This is the backward difference approximation for dy by dt at t is equal to ti. We are looking at one value backwards. This is our base value. So dy by dt at ti is going to be y at I minus y at I minus 1 divided by h. That is going to be equal to f evaluated at the base point, which is yi. Therefore, you can write it as yi is equal to h f yi plus yi minus 1. This is how you can write it. Now, if you just change notation and say I is nothing but n plus 1. What's in a symbol after all, right? So I can replace by n plus 1. So y at n plus 1 is going to be h f at yn plus 1 plus yn. And this, if you rearrange and write it, you will get this form. So basically, for dy by dt, I've used backward difference approximation. Then rearrange the terms to get this. Now please note, this is single step because yn plus 1 depends only on yn. It does not depend on yn minus 1, yn minus 2, yn minus 3, etc. So it is a single step. But this is what is called an implicit formula because yn plus 1, the unknown, appears on the right hand side as well. Previously we saw the forward difference approximation gave us the forward Euler method, which was explicit. That means the right hand side was only a function of yn. The left hand side was yn plus 1, therefore it was easy to compute. But in this particular case, what happens is yn plus 1, the unknown, appears on both sides of the equation. So this is a first case where even for the simple Euler method, because we have chosen the backward Euler method, we have to resort to iterative calculations. So I have to guess a value for yn plus 1, the unknown variable. So this is known, this is given to us. Let's say y0 is given to us. We are trying to find out y1, the value of y at x is equal to x1 or at t is equal to t1. So we are trying to find out y1. So y1 is going to be equal to y0 plus h times f of y1. So what is y1? We do not know. We know y0, we know h, and we know the function form for f. Therefore, what we do is we have to assume a value of y1. Then evaluate f of y1. Multiply that by h, and to that you add y0. Now you will get a new value for y1. You take it and put it back there. And so on, do these iterations until we converge to a value of y1. So that is your value of y1. Seems like a pain, right? Iterative techniques, we do not know how many iterations it will take. We have to give a good initial value for y1, etc. But then we can show that the implicit methods, right, of which backward Euler method is one example, the implicit methods have numerical stability that is much better than the explicit equations. Explicit equations are easy to calculate, but then they suffer from numerical instability, whereas the implicit methods are numerically more stable. That means even for larger step sizes, the accuracy is likely to be much better. To end this video, I just want to say we got introduced to the two Euler methods. One is a forward Euler method and the other is the backward Euler method. The forward Euler method we demonstrated using at least two examples, and it was an explicit single step scheme. And there we saw that as h decreased, the accuracy improved. We just looked at one problem on that, but that was something that we got some idea about. Now this backward Euler method is also a single step method, but then it is an implicit method. That means it requires iterative calculations. And I just said iterative calculations have the benefit of having higher accuracy even if our step sizes are large. But the downside is iterative calculations take up more time and effort. So I'll stop here and catch up with you in the next video. Thanks for your time.